In our last presentation, we talked about the problem of moving a disk drive head to the desired location using feedback control, and we developed a plant model for this application. In this presentation, we'll begin to design the controller. In this example, we'll use a proportional controller. That is, the voltage going to the coil, V of t, is proportional to the error, E of t, through the constant Ka. So V of t is Ka times E of t. Actual disk drive controllers use a much more complex means of determining the voltage from the error signal. However, analyzing this system with a proportional controller is suitable for our introduction to this topic. We'll now find our closed-loop transfer function, and we'll do this by appealing to the material that we covered before when we talked about feedback interconnection. In the top part of our feedback loop, we have Ka and 5 over s plus 20. Of course, these two systems are in cascade, and so we simply need to multiply their transfer functions to find out the transfer function in the top part of this loop. In the feedback part of the loop, which is the lower signal line, I'm not showing a transfer function there. Recall before I showed the transfer function there as 1. Of course, these are equivalent. So if you don't see a transfer function in the feedback loop, if none is present, like in this diagram, then you know that transfer function is 1. So, comparing to our standard diagram, in the forward path, if we had a transfer function g1, and in the feedback path, we had a transfer function g2, and we have negative feedback, then the closed-loop transfer function between the input r and the output y will be g1 divided by 1 plus g1 times g2. For our case, g1 is the cascade combination of Ka and 5 over s plus 20. And g2 is 1. So now we can just simply plug these into our form and do some algebra to find the closed-loop transfer function between r and y. So here we carry out this algebra to find the closed-loop transfer function. Recall that g1 is 5 Ka over s plus 20, and g2 is 1. So we simply simplify the numerator and the denominator of our transfer function, and we'll find the closed-loop transfer function is 5 times Ka over s squared plus 20s plus 5 Ka. That is the relationship between the desired position signal, r of s, and the actual position signal, y of s. Note that the poles of this transfer function are dependent upon Ka, which is our proportional controller constant. We get to choose this value, and by choosing it, we'll affect the dynamics of the closed-loop system. Now let's look at the behavior of the closed-loop system, and what we'll look at is the response to a step input in the requested position. This is basically like asking the disk drive to move over one track. So, if r of t is a unit step, then r of s is 1 over s. And plugging this in, we'll find y of s is the closed-loop transfer function 5 Ka over s squared plus 20s plus 5 Ka times 1 over s. Now we'll use the final value theorem to do a quick evaluation of the behavior of this. And the question we have is, if we ask the disk drive head to move over one track, will it move over one track, or will it move over slightly less, or slightly more? This is what the final value theorem can tell us. So, we'll find the final value, which I denote YSS for steady state. And it's going to be the limit as t goes to infinity of y of t, which according to the final value theorem is the limit as s goes to 0 of s times y of s. When we take the limit as s goes to 0 of s times y of s, we'll find the steady state value of the head position, y ss, is equal to 1. That is, if we request the head to move over 1, the controller will actually make it move over precisely 1, at least at the final value. So y of t goes to a desired position. Now, of course, it doesn't get there immediately. If we look at the response of y of t and compare it to the request, which was a unit step, we'll see there's some transient time, some time when the disk head is moving to the requested position but is not there yet. The behavior during this transient is very much dependent upon the poles of the closed-loop system. It's dependent upon how fast they are and whether they're complex or real. The poles of the closed-loop system are, of course, the roots of the closed-loop system's denominator polynomial, and that was s squared plus 20s plus 5ka. So you see the poles are going to be a function of the parameter ka, which we get to pick. And by picking this parameter, we can influence where the poles are and therefore influence the closed-loop system's behavior. That is, what the transient looks like. Does it happen quickly? Does it oscillate? These are things that are determined by our choice of ka. So let's look at how the closed-loop poles vary with ka. And here we have a diagram which is known as a root locus diagram. It shows the positions of the closed-loop poles as ka is varied. As ka is varied, the closed-loop poles will move along paths in the complex plane. For very low ka, when ka is close to 0, the closed-loop poles will be essentially the same as the open-loop poles. That is, the poles of the transfer function of the plant. This is because when ka is very small, it's like the loop is not closed at all. It's like the system is open loop. Now, as ka is increased, the poles will move in the complex plane, and the motion of the poles in the complex plane with increasing ka is shown by the arrows on the diagram. So, one closed-loop pole is starting off near 0, and another one is starting off at minus 20. The pole at 0 is moving to the left, and the pole at minus 20 will move to the right. The two poles will meet at minus 10, and then for larger values of ka, they will become complex, and then move vertically in the complex plane. So their imaginary values will change, and they will be complex conjugates, but their real value will be constant. For low values of ka, the pole that started off at 0 will still be on the real axis, and will be somewhere between 0 and minus 10. This will be the slowest pole of the closed-loop system, and will be the one that dictates the transient response. Obviously, as ka increases, this pole moves further leftward, and that means that the time constant associated with it becomes smaller. That is, the dynamics will become faster, and that will lower the amount of time required for the transient response. I urge you to verify that the poles of the closed-loop system do move in the fashion that I described. All you need to do is take the denominator of the closed-loop transfer function, that is, s squared plus 20s plus 5ka, and plug in different values of ka and make a plot. You'll see that they do indeed move in the complex plane in the manner that I described. For large values of ka, the poles will be complex conjugates, and this means that the transient will have an oscillatory behavior. So you see from this example that the value of ka is very important to the transient response of the closed-loop system. For small values of Ka, the transient response will have no oscillations, and the disk drive head position will go to the requested position. For large values of Ka, there will be a transient oscillation. Still, as time goes to infinity, y of t will go to r of t, that is, the disk drive head will move to the desired position. The engineer's job is to decide how to pick Ka so as to get the most desirable response. If we were using a more complex controller, then we would have more parameters to tune in an attempt to try to get faster response, perhaps, with less oscillation. With the proportional controller used in this example, we have limited ability to tailor the way the system responds. Let's now investigate how this system responds with various values of Ka. We'll do this using a MATLAB code that I have written. And this code actually computes the response, both for the actual transfer function and for the approximate transfer function that we developed. So we'll try our value of Ka equals to 1 here, and see what the response of the system closed loop is to a unit step. Note that the response is going to 1, as we would expect, since it was a unit step input. But it doesn't fully respond until almost 20 seconds, and this would obviously be very slow. There are two curves in this plot, but one lies right on top of the other. The curves are for the actual system's response and for the approximate system's response. Let's now try Ka equals 10. We'll type that in here, we'll press the green arrow to execute, and we'll find the response to a unit step. And what you'll notice is it's a lot faster now. In fact, it's settling within 2 seconds. Let's now try Ka equals 30. We'll change the value, we'll press the green arrow, and we'll find the response. You'll notice the system is fully responding by about 0.4 to 0.5 seconds. As we increase Ka, the system is getting faster in its response, as expected. Let's now try another value of Ka. We'll change Ka to be 100. And we will execute the program again and see how the system responds in this case. You'll note the response is initially going beyond its final value of 1, and this behavior is known as overshoot. Now, it settles at its final value, still around 0.4 to 0.5 seconds, so we're not really making the system faster by choosing a larger value of Ka in this instance. You'll also note that there's a slight difference between the blue line and the red line, that is, between the approximate system's response and the actual system's response. The overshoot shown is related to the poles being complex now, and this is also why the speed of the response is not improving. Let's now look at one more case. We'll examine what happens when we change Ka to be 1000. We execute the program and we find the response of a system to a unit step. And what you'll note here is that there's a lot of oscillation, a lot of transient, before it settles. The transient looks different for the approximate system versus the actual system. But nevertheless, there still is a lot of oscillation going on. The system's response really isn't any faster. It still takes about 0.5 seconds to reach the final value. You'll note that the overshoot is even larger than before, and this is because the poles in the complex plane have moved farther away from the real axis. The main point that I want to emphasize here is that the response of the closed-loop system depends upon the value of Ka, and that by choosing the value of Ka, we can tailor the system's response. Later in the course, we'll discuss more about looking at the transient response of systems, and how the transient response of systems depends upon the location of the poles in the complex plane.